So the statement of Rolle's theorem is that if we have some function f from the closed interval a, b to the real numbers, and it's continuous on the closed interval a, b, and differentiable on the open interval a, b, and the endpoints are equal to each other, then there exists some real number c in the open interval a, b such that f dash of c is equal to 0. If you prefer pictures, this might help you. So informally, if we have some function on a level set like this, where we don't take our pen off the paper and it isn't too spiky, then you'll always find some point at which the curve is flat. And in our case, this is the point C here. And that's essentially what Rolle's theorem is trying to tell us. That if we draw some function where the endpoints are the same, where we don't take our pen off the paper, and it's not spiky, then we'll always have a point like C. So let's have a look at the proof. We're going to use the extreme value theorem here. If you haven't seen that before, I'll put a link to a proof in the description. And it states that if we have some function f from the closed interval a, b to the reals, and it's continuous on that interval, then it attains both its maximum and its minimum on the closed interval a, b. So we're going to split our proof into two parts. The first part, we're going to assume that both the minimum and the maximum are attained at the endpoints. Now that can be any permutation that you like. We could have b being the maxima, a being the minimum. It doesn't really matter which ones you pick because we know that f of a is equal to f of b. And so if f of a is a maximum, then f of b is a maximum. So necessarily, we have an inequality like this one, where if we just take any c in the open interval a, b, then c has to be trapped between f of b and f of a. This is because both f of a and f of b are maxima and minima at the same time. So when necessary, we can replace them here in this inequality. But of course f of a is equal to f of b, and so this inequality must collapse, and so f of c is equal to f of b and equal to f of a. Therefore f is constant, and if we take the limit here, we can see that this is trivially 0, provided that h is sufficiently small such that c plus h is in the open interval ab. Part 2, we're going to assume that f has a maximum or a minimum, or both, at some point in ab. For now, we'll just assume that it has just one maximum, but the proof is exactly the same no matter how many maxima or minima you have. And so we're going to assume it has a maximum at c in the open interval ab. So we know immediately that f of c plus h minus f of c divided by h is less than or equal to 0 if h is greater than 0. And h is sufficiently small. This just immediately follows from the definition of f of c being a maximum. So f of c must be greater than f of c plus h. And so this implies that if we take the right-hand limit of the derivative, so we'll call that f dash of c plus, and we'll take the right-hand limit here, so as h goes to 0 from above, that must be less than or equal to 0. And so we're going to do a similar thing, but with h less than 0 and h small. And so the inequality is reversed here, just because h is negative. So we have to multiply the whole thing by -1, and we end up with the exact same inequality here. And so f dash of c minus, which is the left-hand limit this time, is greater than or equal to 0 by this inequality. But we know that f is differentiable at c. So the left and the right-hand limits have to agree. So f dash of c minus is equal to f dash of c plus. And the only way that that can happen is if they're both equal to 0. As f dash of c minus has to be greater than or equal to 0, and f dash of c plus has to be less than or equal to 0. And therefore, we've proved the theorem.